you look at the number of K, and you see how big it is, and if it's really big, it favors products, and if it's really small, it favors reactants, meaning that the diffusion reaction does not favor it favors reactants. Okay, so let's actually go with number 3 first before I go over number 5. With this question, I'm sure you read it, number 3. What are we solving for? So the concentration of H2, but how would you go about solving it? What's probably one of the first things you're going to do? Say again? K, the K expression. Oops, this is our worksheet. There we go. So what is the K expression for this reaction? So methanol. CO and H2 squared. Okay. So whenever this goes to completion, whenever it goes to equilibrium, it tells you the concentrations of equilibrium everywhere here. So obviously the one unknown is this H2 right here. So what do you want to call that unknown so that we can solve for it? Let's just call it X, right? It happens to be X squared, but our job is really to solve for X, which is the concentration of hydrogen ion, or hydrogen, we put it in there. So then let's just plug everything in and solve. What is this K number equal to? What's the actual value? What's the value of K? Sorry, what is the value of K from the problem? 1.609. Okay, so that's 1.609, which is given to us in the problem. And then we're going to set that equal to 0.818 divided by, get your calculators out so I can make sure you're participating with me, because I want to make sure you plug in your calculator right. Because yesterday we were, I think, struggling on that one. It may have been fourth period though. 1.402 goes in the bottom. Why am I not writing molarity? Because K is unitless, right? And then I'm going to put X to represent the hydrogen concentration squared. All right, so how do I solve for X squared? Algebra, right? Give me more though. Okay, so 1.609 times 1.402 equals 0.818 over X squared. I got you that far. What else? So multiply X squared on both sides, okay? That's on both sides, so we get X squared times that equals 0.818. Okay, so then divide by this. And you could have gone about it a shorter way, but I'm listening to what you guys say. And this does work on both sides. 1.609, 1.402. So in the end, X squared equals 0.818 divided by these two numbers. Multiply by each other. I'll get my calculator out just in case. Well, what'd you guys get? This is 3626 point. Sorry, I was like, I'm hearing a big number. This is not a big number. Okay. So 0.3626. Now what do you do? Square root, right? So this is going to be, what's the square root of that? You guys have the value in front of you. 0.66. Okay, this is the concentration of hydrogen. So that was just a different type of problem, solving for one of the equilibrium concentrations, or one of the equilibrium concentrations versus solving for the K value. Now let's backtrack to ones that involved ice with our homework, 5 and 6. So I'm going to start with number 6. So I'm going to go back. Yeah. Okay, give me a second. I have to go a little bit out of the way here. All right. So ignore my big check mark. Let's go to number 6 first. So I'm sure you guys set up the K expression. What was your K expression here? So the concentration of just HI, and that squared. That 2 just becomes an exponent. That's the squared. Over hydrogen times iodine. Okay, and that value is not given to us. That's what we are solving for. Ice is set up by writing out your BCE again, because it's just easier to work with. And then your initials were given for hydrogen concentration, 0.020 molar, and the iodine, 0.040 molar. calculate the K if the equilibrium, if the original concentration of H2 was reduced by 0.01. So if it says that's reduced by 0.01, what is that telling you within the whole icebox? Change. Just H2, right? And so you can figure out, if that's the change of H2, you can figure out the change of everything else that's based off the stoichiometry that's represented in the BCE. So you're going to subtract 0.010 molar here. What's 0.02 minus 0.01? 0.01. Okay, so that's just, I'm just going to stop there for hydrogen. We know a couple more things. We know that before a reaction begins, we start with 0 of our product, and then we also know the ratio in which these things react. Well, if this is a 1-to-1 mole ratio, and this reacts 0.01 molar of it, then how much does this react? So what are you looking at when you're deciding that? Are you looking at the BCE or are you looking at the original amounts? You should be looking at the BCE because the original amount, I can have like 1,000 moles of this or 0.0000001 of this. The amounts here do not indicate how much react. It's based on the ratios in which these reactants react. So if I'm telling you 0.01 is being reacted here, I'm going to call that minus X. Well, if they react in the same amounts, I'm also going to minus X here. So what is X equal to in this case? 0.01. So if I'm subtracting the same amount, because it's a 1-to-1 ratio, I'm again subtracting 0.010 moles here. So then this leaves us with 0.03. You got me there? You don't look at the number, initial amount, you look at the BCE just to compare. All right, so then how much is made here in terms of X's? Right, you're making 2X here because that's a coefficient of 2. And we already know what X is worth. It's worth the change amount 0.01, so that I'm actually adding 0.02. And so I'm saying that these two things are equivalent. 2X is equal to 0.02. And so the final amount here at equilibrium is 0.02 molar. And then from here, we would plug that into the into the K expression and figure out what the K value is. So what am I plugging up top here?
0.02.
So what's 0.02 squared? Like 4 times 10 to the negative fourth, because that's 2.0 times 10 to the negative second square is give us a bigger exponent. And then 0.010 down here, 0.03, that gives us 3.0 times 10 to the negative fourth, I believe. Is it 1.33?
No, it'll be 0.2.
On the bottom? Isn't that negative fourth? 0. I did that in my head. Don't just trust me. Do check that. This is like the world's worst calculator. It's like sticky buttons. Is it 1.33? Yeah, thank you. Okay. All right, so what do we know about that equilibrium? And so the extent of the forward reaction is bigger than the extent of the reverse direction. Something like that's another way to state it. Okay, so we were using real numbers here. You know, we said it in terms of X, but then we knew what X is equivalent to. So I want to show you how to do it with numbers that we maybe don't know. It's just an extension of this, but we're actually going to use true X's versus numbers. So let's go through a couple of those, and then I have some examples using pH. This is the first example, and I don't know that I put this one on yours. Did I? No. So how about you write down some givens here? Write down BCE specifically with your given amount. And as you're reading, tell me what's different about what's given in this problem.
Reading.
All right, so it's giving us moles and liters, right? So what do we need to do to that information? Knowing what unit have we been putting in all of our ice boxes? Molar, right? So molarity. So ice requires molarity, and that's because the whole deal with the concentration of products over the concentration of the reactants, it requires concentration. So you know we're probably going to have to take our moles divided by our liters, which is just 1. It's easy math. What else is given that's usually not given in this case here? The K value is given, right? What are we not given at all? So HI information or information about what's present at equilibrium, correct? So we're going to figure out what's at equilibrium in like kind of algebraic terms, x's versus real numbers. So from here, tell me what we know. What's our initial concentration of hydrogen? So 0.2 moles over 1 liter, isn't that just 0.2 molar? Right, so that's 0.2 molar. Iodine is the same, 0.2 molar. And that takes care of those in the whole liter deal here. We are originally given nothing for hydrogen iodide, so we're going to actually call that 0 for now. And then, before I go too far, I didn't set up something. What do I always set up first? K expression. What is this K? So K is 49.5, by the way. What is the expression equal to?
2HI, or HI.
HI squared over H2 and I2. We've written that one like 3 times now. Okay, so that's what this whole shebang is equal to. So whenever we don't know what's happening in the middle, we just call them X's like we kind of have been doing, but now for real. How many X's are subtracted from each reactant? I heard it. How many X's are subtracted from each reactant? Why 1? Because it's a coefficient of 1. You subtract in accordance with the coefficients. Minus 1x, minus 1x. What do I add here? Remember, I'm taking away reactants to add products. 2x. All right, so at equilibrium, we actually have some funky looking stuff. We have 0.2 minus x, 0.2 minus x, and 2x. These values go into our expression now, and then we have to solve for x. So I'm thinking, it kind of looks like I might be going quadratic formula. Negative b. Nobody knows the song? Okay. No, don't sing it. Don't sing it. We hopefully will not use the quadratic formula. Our goal is not to do that hard of math. Chemists don't want to do that kind of math. We want to simplify as best we can, and we can simplify. So these values go in here. So 49.5 is equal to what goes on top. What's going into the HI? 2x parentheses squared. What is that when I distribute the 2 or the squared? 4x squared, right? So it'd be 4x squared. Okay, so think about that in a second. And then over what? 0.2 minus x. My little x gets in the way. Minus x. That's for the h. And then why are you squaring it? Because there's 2 of them. And I'm going to show you that like this. Okay, so 2x squared over 0.2 minus x squared, because you can combine those. So what's the easiest way right now to simplify this and 49.5? Right, well that basically means you're square rooting it, right? So just cross out the squares, you square root the whole thing. If you square root the whole thing, your math gets so much easier. So what's the square root of 49.5? Calculatora. You guys are my calculators because mine is wacky. What is it? 7.03, okay, 04. That equals 2x over 0.2 minus x. Okay, we can do this. How do we solve for x?
Divide by 2x.
I can't divide by 2x right now. Yes, this is a function or something like that. It has to stay together. So you have to multiply this on both sides. So then you'll get 7.04 times 0.2 minus x, because I'm multiplying it on the left side and I'm multiplying on the right side. So I'll write it out for now. Here's what I'm doing. And so it crosses out on this side. And so 0.2 minus x times 7.04 equals 2x. So what do I need to do now? Distribute, and then what? Combine like terms maybe first and then divide by 2? Or divide by something. So what's 7.04 times 0.2? 1.408. and then 7.4. So basically we're going here, and then 7.04. So I'm subtracting 7.04x when I distribute that out equals to 2x. Now combine like terms. There you go. Does this just look like straight up algebra? So my math people are like, hallelujah, back to some math here. And my non-math are like, what in the heck have I taken? Okay, so now that I'm to 9.04x, I need to divide by 9.04. 9.04, and x is equal to what? I think that's a little off. 1.4.
I got 1.5 or 0. I mean 0.
0.115.
1.5.
1557. I hear like everybody's numbers. I can't pick it out. 1557. That makes more sense because it's like 2 divided by 9. Okay. This is the concentration of what the heck did we just solve for, guys? Concentration of what? None of them. That's just x, right? So what's the question again? What are the concentrations of iodine, hydrogen, and hydrogen iodide? So we found x though, right?
But wait.
So what do we need to do? Apply the x here, here, and here. All right, so tell me what those are. You know what x is. There's x. So hydrogen is the same as iodine. So that minus x gives us 0.044, all around 4 molar. There's our hydrogen iodine. I don't know why I circled the whole thing, but I did. And then hydrogen iodide is worth 2 x's. So that times 2 is 31016. Okay. So the last step really wasn't that hard, but you're like, why did I do this? I got down here, and then what do? You just have to refer back to the question to see what the heck x is meaning, what does it mean to you. So this is a high level question. So you have to understand how to apply the K expression. What does the K expression mean? How to set up an icebox, do some algebra, figure out what x stands for, and then reinsert x where it belongs. So this time we solve for x versus being given x. This is a typical AP Chem problem. Okay, so let's stop on this icebox. Let's go to one with pH. Okay, so we can do iceboxes with anything, any reaction. And sometimes if we have them in the reference of acids and bases, we actually can find out more about them by actually plugging in our old pH formulas and finding out the concentration of the particular acid of interest. So we're going to start with nitrous acid. This is number 1 on the lecture examples, calculating equilibrium. You see it down there? Number 1 on the bottom right for you guys. So these things are like super itchy. Like scratching me. So we're going to talk about nitrous acid. We're going to write out an expression write out a reaction where it reacts with water. So tell me what nitric acid is first. Nitric acid. It comes from 8. Okay, so nitric acid is HNO3. So what's nitrous acid? HNO2, okay? So I'm telling you the Ka value of this. The Ka is just a K value, is 4.5 times 10 to the negative 4. What does a really low K value tell you? Favors the reactants, right? It also tells you something about the acid. It tells you it's a weak acid. So this Ka value for nitrous acid is really, it's telling you it's a weak acid, but you already knew that was a weak acid. How? Because it's not one of the 6 strong ones, right? So let's actually set up the equation for this first, and then we'll solve for the pH. This is reviewing pH because I want to make sure that I helped you guys there since that was a week ago. So the very first thing we do is write out nitrous acid reacting with water. And I want you to make it act like a bad acid. Okay? Tell me what it does. What do bad acids do? They do what? They donate what? A hydrogen, right? So this is serving as a review right now too. I know some of you guys are like squinting your eyes and you're like, what is she talking about? Bad acids are peroxide acids, which are donors of protons. So who is it donating the proton to? Water. So this H plus is going over here. So what does it make? H 3O plus, right? Because it's got an H plus, so it carries a charge with it, and it gives another H to it to make H3. And what's left behind? NO2, 1 minus. Okay, so that's our BCE, for step 1 BCE. Step 2, set up icebox with initials where we know them. What do we know? What do we know? Where is that going to go, though? Under nitrous acid. That's the only thing we know right now, right? And does liquid water get involved in this at all? No, it's a pure liquid. I just go ahead and put a scribble through it. It's there simply to help me balance, but it's not there for really any other reason. What do we know about both of our products? 0, 0. Okay. I also know my K value. Can I go ahead and set up something? K expression. Ka is equal to, whenever you're ready. So hydronium times nitrite over nitrous acid. Okay, so if I can get these equilibrium values, I will. Actually, I don't really need to solve for K. I know what K is equal to. It's equal to 4.5 times 10 to the negative 4. Okay, so before we get too in-depth here, what's the real question here? It says what's the pH, right? But when it's asking for the pH, what do you really think it's asking for so we can then calculate the pH?
Concentration of H.
Right, so the real question here is not what's the pH, it's what's the concentration of hydronium. So I'm going to put a red circle around this to remind you that this is the important piece here, because we can calculate pH, we know how to do that. It's just negative log of the hydrogen ion concentration. So let's figure out what that is, and I think we're sitting pretty here, okay? So since I don't know what's happening, I do know that this is reacting, but how much is reacting? Good, nobody knows. So what would you call it? X. Since you don't know how much is reacting, you get to call it X, okay? So minus X. What do if I'm subtracting 1X here, what am I adding here and here? 1X and 1X. And remember, you're subtracting from the reactant side and adding to the product side because you're making products when you react reactants. So then at equilibrium, we have 0.002 minus X. You have X, and then you have X, right? So the beauty of this is if we solve for X, we have our question. We just need to do the negative log of it to get our pH. So then how do I solve for X? Right, these values get plugged in here, and I'm just going to do it over here in red. So the top numbers, X and X, what can I simplify that to? X squared over the bottom one, 0.002 minus X. Okay, I'm going to show you guys a cheat sheet in your calculator. Has anybody ever used the solver? Okay, there's a solver. Okay, all my AP kids did not know this, and they're for like almost seniors. Okay, come on. So, math, on your calculator, math, and it says solver, I think, down at 0. So look on it with somebody. This is a good way to check a complex problem. Some of you who have different calculators, y'all tell people what to do here.
This is summation.
Keep going down. I don't know. Listen to Hannah. Hey, can everybody find solver? Okay.
First clear.
Okay. So when you go to solver, I know your math teachers are going to be really mad at me, but here we go. When you go to solver, it says 0, right? Okay, so when it says 0, it wants you to set up some sort of equation or formula equal to 0. So if this is our stuff we're working with, you just need to subtract this and put this on the other side. So 0 is equal to X squared over, parentheses, 0.002 minus X, end parentheses, minus 4.5 times 10 to the negative 4th. And then you hit enter. I have to look at somebody's. Look at Sally's. This is the one. I only know how to work like 2 versions of the calculator. I don't know how to use them either. We'll look it up. And that looks good. So once you hit enter, it'll say X equals something. You have to put a number in. Usually the number is 10 that they give you. then you must hit alpha solve. If it says 0, put in a number. And put alpha solve, and let's see what it says. Solve is the same as enter. Negative. It should give us a negative number. Oh, you have to put parentheses around your 4.5 times 10 to the negative 4th. Oh, sorry. Go back up. I can only help people with calculators that I know. Yep. Yeah, I don't know how to do that one.
Okay, now.
Oh, that's fun.
Doesn't work.
What do we do with alpha?
I don't know.
Maybe because enter? Did you try by saying enter?
Are they ready to get an
Oh wait,
answer?
I got 49. I got one to
I have a question. What's supposed to go in bottom?
I don't know. I don't know. Once you figure it out on your list. I got 16.
What? How'd you do that?
I know.
What? What did you click? I got.
I got 16. Okay. The answer is not negative, by the way. The answer is
got
not
10.
16. Let me. The answer is not 10. You guys are making me solve this.
Yeah, what'd you put in the bottom?
You didn't figure out how to do it.
I put 0.
Yeah, that's your problem.
Your math teacher's gonna hate me.
Not if you can't figure it out. This makes me so sad. I'm so close.
This calculator. Ooh.
No.
All right. I'm gonna try.
Is it okay, but how do we get to that?
These are insane. Where's X? I don't even think. I'll solve it with another
I
calculator.
got
All right.
10 again.
Pause on that for a second. Let me just finish this problem with a number for you first, and then I'll show you. So let's say X is equal to 1 times 10 to the negative 6. When you get it, it's gonna be. It is gonna be something very small. For some of you, it's showing up as negative, which I'm not really sure why. I don't know that I don't think I made up that Ka value. I might have, but I probably didn't. I probably looked it up, actually. But if we got a really small number, it should make sense because whenever weak acids dissociate, they don't do it very much. So this is going to be predominantly still there. You're going to make very little of both of those. How do you find the pH if you know X is 1.0 times 10 to the negative 6? So this X is equal to hydronium, right? So it's the first thing to make clear, like this is equal to hydronium. And then from there, pH is equal to negative log of hydronium, which is negative log of 1 times 10 to the negative 6. And you can do that in your head. What is the negative log of 1 times 10 to the negative 6? Take a guess. 6. The answer is 6. Because the exponent, when you have a 1 in front, the exponent is the pH when you're utilizing hydronium. So tell me, does that make sense for a weak acid? Yeah, that's like super weak. It's almost neutral. It's so weak, it's almost neutral. So with the real answer, it might be like 4 or 5. But that's basically how you set up a reaction with an acid. You do an icebox with a given concentration, and then you use X once you get it in some way or form. You can also do this via the quadratic formula. There's actually another way to do it, and I might not tell you guys that right now, to find X. Okay, so I think that's all I want to do right now. We actually might not get to our virtual lab. Let's talk about Le Chatelier's principle. This is the last main topic we need to talk about, and I have to write curriculum for the county for every chemistry teacher who teaches chemistry tomorrow, and they've asked me to go there, so I have to talk about Le Chatelier's today so you guys can practice tomorrow. So I'm sorry, I'm saying I won't be here tomorrow. Okay. But my AP Chem students are tutoring during Teal A. Okay? So they have already got like 6 or 7 volunteers. Le Chatelier's principle, yeah. Friday. So we're after today we're done. I'm going to tell you what else I want you to do on your sheet, but it's not very much. If you're not going to be here Friday, take it Thursday, or you're taking it the day you get back, which might be unfortunate. I don't know. I don't know if that's a good idea, but you're going to have to, right? So Le Chatelier's principle, what do you remember from that, from your simulation? From your web quest? Okay, so there's an example with ammonia. What else? Okay, so they're changing pressure and temperature, and they're causing reactions to shift left and right. Yeah. It changes to alter it, right? So guys, if you get stressed out, right? You get really stressed out. What do you try to do to come back to your happy place? Okay, deep breath. Okay. Do you try to remove that stress? If you possibly can. If your stress is, you have too much homework, you try to alleviate that stress by maybe doing some of it, or just, I don't know what else you would do. You would not do it.
Throw it out.
If you were stressed out because you were running and you were running out of oxygen and you're like, oh my gosh, I can't breathe, you'd probably stop running and take a breath or something, right?
Just keep going.
Okay. If you're stressed out because you're really, really hungry, lack of food. I don't know, I get stressed out when I'm hungry. I also get hangry. Okay, then you eat, right? So anytime you have a stress, you always want to do something to fix that stress. Well, in equilibrium, the stresses can occur by either changing reactants, changing products, changing pressure, changing temperature, and the reaction has to do something. Shift left or shift right, meaning go towards the reactants or go towards the products to get rid of the stress. It's a very easy concept. I just want to do a couple of examples with you. So, things that you could do, and I'm going to show it to you actually. I'm going to show you from an example versus this, and I'll come back to this to give you some background information. Okay, so let's look at this example. I don't know that I printed this one for you. No, so write this down in the extra space on your back of your note sheet. Write down this example. And so remember, the main concept of this is to fix the stress, remove the stress, alleviate the stress, whatever term you want to use. And the stresses are the ones that are following the bolded print here. So we have nitrogen plus 3 hydrogens equilibrate to 2 ammonias and 92 kilojoules of energy. So I'm going to teach you some through this, and then we'll go back to the written part. So the first stress you can see is that I'm heating the reaction vessel. And the reaction vessel is just the place where this reaction is happening all together. And so if I heat the reaction vessel, I'm adding heat. Well, where do you see heat in this reaction? Is it a reactant or is it a product? Right, and you're seeing it as energy, because heat is just energy, it's thermal energy. So I'm going to call this heat for now. What kind of reaction is that, endo or exo? Exo. Okay, so I'm just going to write that over here just for kicks and giggles. All right, so adding heat basically means adding a product. That's kind of what's happening here. So here's the best way I've talked myself to do this, okay? Oh my gosh, I've got too many products. I've added a product. What do I do to get rid of products? Do I reverse the reaction and go back to the reactant side, or do I go to the forward direction and make more products? You go back, right? So remember, whenever I'm going to write this down as shift left, okay? So this is shift left, that's what I mean by SL. Whenever I want to get rid of something, I have to consume it. I have to use it up. So if I want to use this up, I must go away from it. I must shift away from it. I must use it up as I react in the reverse direction, reversible or in the reverse direction. You with me so far? Some of us are like, oh, I'm not sure. Okay, so let's skip down to this one. I'll come back to the pressure one. If we remove ammonia, so this is actually removal of what? Right, and you'll see ammonia as a product. So I'm going to write removal of product. So if I remove a product, what's my cry for help here? Oh no, I've got too few products. What do I need to do?
Go forward.
I need to make forward. I need to make more. I need to go forward, right? So I need to make more by shifting right, by going to the right side. So you're always trying to fix the stress. You're trying to alleviate the stress. Try to do so you can see all of it here. Okay, so removal of product. I need to make more products, so I shift right. Who got that one? Thumbs up. Okay, this is very conceptual, okay? Now the next one is add excess hydrogen, okay? So what am I adding technically here? So I'm adding hydrogen. A reactant, right? So adding a reactant. So then my cry for help is, oh no, I've got too many reactants. What do I need to do with them? Use them up. So how do I use them up? Make more products, right? So if I use up reactants, I'm making products. That means I'm going to the right. So I'm going to say need to consume or use up reactants. So that means I need to proceed towards products, which just means shift right. So I'm giving you some of my explanation, but the answer to like what's happening are the shift left and shift right answers. All right, so the pressure and volume ones are interesting because you guys have your box of air. I forgot to tell you to bring it. Oh gosh, okay, I was scared. Box of air. All right. I'm going to go to the volume one here, okay? If you decrease the volume, what have you just done inside of that box? You've increased the pressure like crazy, right? So you have actually stressed out the system by increasing the pressure. What do you need to do to alleviate that stress? First, well, okay, you can't change the volume, okay? Don't change the volume. The only thing you can tell me is shift left or shift right. That's all you can tell me, okay? So here's the thing. If you've increased the pressure, your job is to fix the pressure, correct? If you've got to fix the pressure is just caused by collisions of the container wall. So how do I fix pressure? How do I make pressure less? Let some stuff out. I can't. This is a closed container. Nope, can't. And remember, I'm only able to shift left or shift right. I can't change heat. I can't change that kind of nonsense. So I want you to tell me step by step. I want to decrease the pressure. And pressure is caused by collisions with the container wall. What do I need inside?
Less particles.
Less particles. Less particles would collide less, and they would cause less pressure. We got that. Okay, where are less particles in existence? Reactant side or product side? Product side. How do you know? Because the coefficients matter. There are 2 molecules of gas here, or 2 moles of gas here, and there are 4 moles or molecules of gas here. And it's all dealing with gases. Solids don't cause pressure. They're chilling on the bottom of the container. Liquids don't either. They're just kind of wavy. Gases are what you're looking for. So you guys figured that out. Great. That was a little bit of a hard one. So basically, let's walk through the domino effect again. Decreasing the volume does what to pressure? Increases the pressure. You're like, I need less pressure. That's your goal, right? So if you've caused the pressure increase, you need to fix that by decreasing the pressure. So to do that, you're like, I need less particles. And if I needed less particles, I believe it was the right side, right? Because it was 4 particles versus 2 particles, so we need to shift right. You see the thought process here? It's a long thought process. But do you see that's the same as increasing the pressure here? So I could either tell you to change the volume, or I could tell you to change the pressure, but in this case, changing the pressure, increasing the pressure will actually result in the same thing. Yeah?
What if you increase the volume? Does that stress it out or not?
Yes, if I increase the volume, what happens to pressure? Less pressure. And you're like, oh no, I don't have enough pressure. What do I need?
More pressure.
I need more pressure. How do I get more pressure?
Shift left.
Well, more particles, and that happens to be on the left for this one. Okay, look on that sheet in front of you. There are 4 example problems, and they're all Le Chatelier's related. How about we start those right now, and let's see where we are, so I can figure out if this is what you need to do for me now or later. I'll go through number 1 with you after you start. 1 through 4.
Yeah, please.
Oh, great question. Okay, I'm gonna wait for everybody. One more time.
Molecules on both sides.
So if they're same particles or same molecules on both sides, this is when you say no shift. Huh? It's no shift, okay? You literally say NS, no shift. Just gotta be careful. Make sure you get that shift in there. You guys are trying to learn the one on the board is the one that's first thing to do first. This is easy homework, but I'm going to start now right now.
There's no NaCl in that. So.
Oh my gosh, I'm going to talk. Go through as many as you can. We'll go through some of them right now. What are you adding? I hear you. I want to hear it again.
I'm talking about the first one.
This one? The NaCl?
Oh, but I was talking about how you're adding another. What is that A?
Oh.
Let's talk about G for a second. You add more to the left side.
Well, it doesn't. So, quick note before you keep going, my bad. The reaction vessel is where all this is happening. This is present, and this is present all in the reaction vessel. The reaction vessel is not where only the reactants are in existence. So the reaction vessel is like a flask, and all of this is in the flask together. So if I add anything, it's not just to the reactants, it's just to the vessel, it's just to the flask. So I already heard some talk on the NaCl one. Let me go ahead and explain that one. Do you see NaCl in the reaction?
No.
No. Do you see Na plus in the reaction? Do you see Cl minus in the reaction?
Yes.
No. It's got to be just Cl minus. So if this isn't in the reaction, you go further. You're like, is it Na plus? No. Is it Cl minus? No. So guess what that does?
No shift.
No shift. It doesn't do anything because it's not affecting anything in the reaction.
Okay. Sorry.
Just because it's not present. Or there's nor is there anything there that's remotely close to it.
It would, yes.
Alright, it looks like a lot of us are almost done with the first one. Give me a second. Tell me your thought process on, actually, tell me your answer on A.
Shift left. Shift left.
Okay, so your thought process is, I've increased the temperature, right?
Yes.
What do I have too much of?
Energy.
So products, right? Too many products, how do I get rid of them? You go away from them, you shift in the opposite direction. Because if you go to the right, you're going to be making more, and that's just going to make the problem worse. You got to get rid of products, so that's a shift left. Okay, decreasing volume.
No shift.
Why no shift?
Because they have the same number of parts.
Right, because there's 2 moles of gas here, and there's 2 moles of gas here. Therefore, it's no shift because there's equal amounts. So changing the volume doesn't favor one side or favor the other. Adding HCl.
Shift left.
Why?
Because you have extra products.
So you're basically adding products. You're like, I've got too many products. I need to get rid of them. And that would be proceeding in the opposite direction so that you consume them. So sometimes you got to talk to yourself through these. I do the same thing, okay? Because I'm like, okay, I've got too many. What do I need to do? Get rid of them. All right, removing chlorine gas.
Shift right.
So what's the problem here, Suzanne? If I remove chlorine gas, you don't have enough reactants. What do you need to do? So you need to make more of them by shifting to the left. So if you remove reactants, you've got too few of them, and your job is to make more of them, but you can't just add them in there. You must either make more of them by shifting to the left or shifting to the right. Who got 5 of 5 here? All right, so we got to keep practicing. Okay. if you want to continue, the homework is actually finishing worksheet 3, which is right below that, and then up on the other side. Alright, we done with 2? Alright, let's check 2 then. Increasing the temperature, what happens? Shifting right, because temperature is kind of like a what in this case? A reactant or a product? Reactant, because temperature is energy, and it kind of aids in creating energy. So energy is increasing, you're like, oh no, I've got too much energy, and so I need to react it by shifting to the right. Yes, ma'am?
What if there's not energy written in the equation and it says like increasing?
It will say delta H someplace. So this one, I'm putting the energy in the reactants or the products, but if you look on the worksheet, hold on, I'm going to tell you which one it is. Look at worksheet 3 right underneath where we are working currently. Do you see the first one where it says delta H is equal to negative 27 kilocalories? Negative 27 kilocalories, endothermic or exothermic? So negative means exiting, so exothermic, right? So then if you see a negative, you realize it's exothermic. Are you going to write the energy on the reactant side or the product side? Product side. And that's how you can figure it out from a delta H. All right, so back here. Increasing the volume. Increasing the volume. And if you need to write down little baby steps like I do, it's very helpful. Decreasing the volume does what to the pressure? Increases the pressure. You're like, I've got too much pressure. I need... No, the problem is I have too much pressure, people. I don't want any more particles. So I'm going to write this out. I need less pressure. So less pressure means I need to make less particles. Yes. Oh, my bad. Sorry. You know. I heard increase, and then I was talking about pressure there. Increase in volume does what to the pressure? Decrease the pressure. You're like, okay, I've got too little pressure. I need to increase the pressure. And how do I increase pressure? Right. Oops. Need more particles, which is to the right side. So that's a shift right. Adding helium. All right, you don't see helium anywhere, right? Okay, now I want you to label this as an inert gas. Inert gas. So anytime you add a noble gas, usually the noble gas is an inert gas, meaning what? Right, it doesn't react with anything. It's just chilling in the container. It actually increases the overall pressure. Sorry, it increases the partial pressure of everything, but everything is actually still at equilibrium. So this is a no shift. Oops, no shift. Adding carbon monoxide. So when you add carbon monoxide, what are you technically adding? What? A product. If you increase products, you need to then alleviate that by decreasing products, which means you shift left. Okay? Heating the reaction vessel. Same as increasing temperature, right? So shift right. And I've already talked about that one.
When you say reaction vessel,
It's just like a flask, all this stuff is hanging out in. Everything's in there together. Yeah.
can you explain how to do the problems on number
14.
14?
Yeah. Yes, ma'am.
So for increasing the volume, do you not count like the coefficients and
You do, and that's what I did here. Increasing the volume decreases the pressure, so I need to get more pressure, right? So I need to get more pressure, meaning I need more molecules. There are 2 moles of molecules over here. There's only 1 mole of molecule over here. This is number 2, indicating the question we're on. So 1 mole of molecule versus 2 moles of molecules, that's going to give us more collisions in the container. That's going to give us more pressure. So that one was a shift right. Shift right. Sorry, I labeled it over here because I ran out of space. Shift toward the more moles of gases.
Okay, so you shift towards the more particles.
Because if you need to get more pressure, you need more collisions, and that means you need more particles. All right, I'm doing number 14 on the worksheet, guys. Okay, so I'm going to scooch away from the ones on the left. I'm going to the ones on the right. So let's go down here. I'm basically doing some of your homework for you, so make sure you're with me, okay? This big, huge reaction, nobody knows what it is, it's fine, we're leaving it as is. What would happen to the concentration of each? So this utilizes a bit more information. We know we can figure out the shifting, but you just need to apply if it's being consumed, then the concentration's going down. If it's being produced, the concentration's going up. So if PN5O3 was added, what am I technically adding? A reactant or a product? Right, so I'm adding a reactant. Does that cause a shift left or a shift right? Give me a vote. Shift left, shift right. Okay, thank you. Shift right means this is going up, so I need to consume it to get rid of it again. So I'm going to shift right. So as I shift right, what am I consuming? I'm consuming all the reactants. So all the reactants concentration, shouldn't they go down if they're being used up? Yes. So CO is going to go down. PN5O3 is going to go down because it's getting used up. But the other ones are going to go up because they're being produced. If you're going towards their side, they are being produced. Okay, so once you figure out the shifting, you have to just say whatever I'm shifting away from is going down, what I'm shifting towards is going up. I think that should help you with the rest of those. Yeah.
So even if you add something and you shift away from it, it'll still go down?
It will, because it's going to be consumed. So you're going to add some. I don't know if you're going to add a ton or if you're going to add a little bit. So usually we don't talk about how much is added. We just talk about overall. Even if stuff is added in the end, it's going to decrease. It may not decrease from its original amount, but it's just simply going to be consumed. You're just talking about like the action of it. Yeah.
Can you purposely put C-3PO in, like the Star Wars character?
I did not think about that. Who's seeing Star Wars on Saturday?
No.
I mean Friday. I mean Thursday night.
So next month.
Okay, never mind. I'll see you there. I don't know, my husband's... We have to watch all 6 before, though. Before. Okay, so how about the last bit of class? Let me make sure I don't want to do anything else with you. You guys are working on the rest of 3 and 4 if you've not already, the worksheet underneath it, and the worksheet to the side. So basically this whole top section is what's for homework, but I want you to finish what you can in class. We've done about half of it, or a bit less. Okay? So let me make sure I don't have any other notes I need to review with you, because this should be the end of our notes for the year. Oh my. I'm just doing a review after this. I'm not reviewing, like, new stuff. Please do not waste your time in class, or I will take it back. Thanks.